We'll be using the periodic table a lot during this school year, and this is a wonderful website, ptable.com, that I encourage you to bookmark on your computer and to use a lot. We'll be talking about it in class. The periodic table is a very dynamic document. It can tell you a lot about things that you never thought possible, and you'll gain an appreciation as we go throughout the year. So some basic understanding of the layout. It's in a grid form, so there is y-axis and x-axis values. This y-axis, these y-axes are called columns, the up and down things. The columns are also called families or groups. So as its name suggests, anything that's in the same column shares very similar chemical characteristics. Anything that's in a row is called a period. So periodic, there's this periodicity, this repeating pattern to the table and the elements that go along with it. So it's in a column, family, or group, or you also have the row or the period. Make sure that you can remember those different terms so that if we refer to them either as families or groups or columns, you know we're talking about the things that go up and down. And anytime we talk about anything within a period, we're talking about something that's in the same row. You'll notice that the elements have these top numbers to them. So a couple of things, each of the elements here has just one capital letter. And then if there are two or more letters after this, and it depends on which table you're looking at, that second letter is always lowercase. It has to be lowercase. So you can tell right away when you're looking at a formula how many different elements there are in it simply by counting up the number of capital letters that are in the formula. You'll notice that the elements are arranged in increasing order if you look at the top number right here. That top number is probably one of the more important numbers of that element. It is what we call the atomic number, or it's also the number of protons in that element. And it's always a top number. Sometimes it's tucked away in a corner, sometimes it's going to be above this centered, but it's usually that number, and it's always a whole number. So if you're looking at the two numbers that you see here, whatever is the larger, whatever is the whole number is always the atomic number, and it's the number of protons. Oftentimes there will be another number underneath, and that oftentimes has non-whole number decimals coming after that, and that's going to be the mass, the average atomic mass of that element as found in nature. So very few of these are whole numbers. First one that we come across is 43, technetium. And it turns out that these are elements that are only found in things that we create in a lab in high enough numbers. So technetium can actually be found in really, really small quantities in asteroids and in really deep portions of the Earth, but in order for us to actually get a hold of it, we oftentimes just have to make it in the lab. And as a result, there's only one isotope that we tend to have. Underneath, you will also find the name of the element. Right? Not all periodic tables will have the name of this. You won't have to memorize the periodic table. That's a waste of time. But as we use the periodic table a lot, you will start to become very familiar with the names and symbols of a lot of the commonly used elements. For example, you probably already know that oxygen has its element and the symbol is O, or carbon is C. So those are things that you already know and nobody told you to memorize them. So a couple of things that are important. Here, this light green area right here that goes from boron and is kind of a stair step and goes between these two elements here and here, that is what we call the Zintel boundary. And the Zintel boundary separates the left-hand side of the periodic table, which is the bulk of the periodic table, from the right-hand side of the periodic table. So it's this diagonal line right here. Now, the main basic differences between the elements on the periodic table, you can see right here. There are metals and there are nonmetals. And this light palish green part of this, that's the Zintel boundary, are the metalloids. Those are the ones that really can't make up their mind between whether or not they're metals or nonmetals. Sometimes they act like metals, sometimes they act like nonmetals. So the left-hand side of the periodic table is the metals, and the right-hand side is the nonmetals. And if you ever forget, again, this is not something you have to memorize, pick something that looks familiar, like, oh, copper. I know copper's a metal, so wow, that must mean that it's in the metal side. Everything along this side from the Zintel boundary has got to be a metal. So one of the things that should just jump out at you is that most of the elements in the universe are metals. That's kind of crazy, right? You'd think it might be half and half, but it isn't. So you may ask, well, what makes something a metal or a non-metal? And the basic definition of what makes a metal is a metal, when it reacts, will form a positively charged ion. And non-metals will form negatively charged ions. We'll understand why later on when we start to understand atomic theory in greater detail, but by far most of the elements that are out there when they react will form positively charged ions. Very few will form negatively charged ions. So the first basic distinctions are the columns and the periods, and then metals and nonmetals. Another thing that you'll notice in the periodic table is that it will tell you states of matter at room temperature. All of these are always at room temperature because we're assuming you're working in a lab, and most labs are at room temperature. So black is solid, and that's true on almost all periodic tables. Black means that it's solid. So again, the bulk of all the elements that you see in the world are going to be solids. Red is gas. So there are not many gases. This whole column are gases. In fact, they are called noble gases. And then there are other ones that are probably more familiar, like hydrogen, nitrogen, oxygen. Maybe you've heard of fluorine and chlorine gas. And then a very few number are going to be blue, and those are liquids. So on this periodic table, it's mercury and bromine. Some periodic tables are at 25 degrees Celsius, which is slightly warmer than room temperature. And so then gallium will also be blue as well. So it really depends on which periodic table, and oftentimes you have to just sort of check, but for the most part, most of us aren't even working with gallium, and so we don't have to worry about that. Another thing that's interesting is that all of these masses are what we call relativized, meaning they are all relative to a certain element. And oftentimes that's either carbon being 12 grams per mole, or oxygen being 16 grams per mole. And as a result, depending on which one they're relativized to, all of these mass numbers may be slightly different on another periodic table. But it doesn't matter, because everything is done by mass ratios anyway, as a way of being able to think about particle ratios. We'll get into the nitty-gritty of that later when we start talking about how to understand masses and stoichiometry. So this is a neat thing about this periodic table, is that you see all the different colors. So within the metals, you'll notice that there's different colors. This first column are called the alkali metals, and they tend to take a +1 charge. Column 2 are the alkaline earth metals, and they tend to take a +2 charge. Everything from here, from the second column onward to the Zintel boundary, are transition/post-transition metals. They're just weird, and in fact they have their own subchemistry to it. This group here, this pink group up here, are called the outer transition metals, which may be weird because they look like they're on the inside, but in reality, this group of 28 elements actually fits into this space right here. So if I really put them in there, my periodic table will be about twice as wide as it normally is. So usually they take it out, and this is kind of like the caret symbol, insert here. And so these go inside this space here, so that's why these are called the inner transition metals. Right, so these two things are right down here, and then the transition metals are kind of like around it, just to understand this grid up here. And then these are the post-transition metals. They are still metals, and they have many characteristics that are like transition metals, but they're not technically transition metals. And that's about all that we're going to cover. I encourage you to look at the different, oftentimes when we start talking about periodic trends, I will have you look at the properties and look at the different properties, and this has a great way of showing this. And then we'll talk about, when we talk about orbitals or isotopes, this tells you how many different isotopes there are. This is kind of crazy because Mercury has 11 different isotopes. And then the compounds that they tend to form. So iron forms 332 different compounds, which is kind of crazy. But oxygen beats it out handily, and carbon does as well. Carbon has at least 40,112 common compounds that are created. So this is, again, an excellent site, and you should bookmark this on your computer, and we will be sending you back throughout the year to just kind of play around with this site to gain some insight into it.